Hi, this is Alex from devstories.eu, Kubernetes and Helm Fundamentals, Episode 3 of 10. You build a container, test it locally, and hand it to Kubernetes to run, but Kubernetes absolutely refuses to deal with your container directly. Instead, it demands you wrap it in an entirely different abstraction first. We are demystifying pods, the actual unit of work in this ecosystem. If containers are the standalone whales of the traditional containerization world, pods are the cohesive groups they swim in together. A pod is the smallest, most basic deployable object you can create and manage in Kubernetes. It represents a single instance of a running process in your cluster. You might wonder why Kubernetes introduces this extra layer instead of simply managing containers directly. The answer lies in abstraction and shared context. Kubernetes needs a uniform way to handle networking, storage, and scheduling, regardless of the specific underlying container runtime you use. By wrapping containers in a pod, Kubernetes treats the pod as a logical host. Here is the key insight. A pod does not just wrap a single container, it establishes a shared execution environment. While a pod often contains just one container, it can hold multiple containers that need to work together closely. When multiple containers are placed inside the same pod, they are guaranteed to be scheduled on the exact same physical or virtual machine. More importantly, these containers share the same network namespace. Every container inside a single pod shares a single IP address and a single port space. Because they exist in the same network context, they can communicate with one another simply by using localhost. There is no need for internal DNS lookups or complex service routing just to get two local processes to talk. If container A binds to port 8000, container B in the same pod can reach it at localhost port 8000. This shared context extends to storage. You can define shared storage volumes at the pod level. Once defined, any container inside that pod can mount those shared volumes into its own file system. This allows tightly coupled containers to read and write the exact same files seamlessly. Consider a primary web server container. Its job is to serve HTTP traffic, but it also writes raw access logs to a local directory. You want to ship those logs to a central monitoring system, but you don't want to bloat your web server image with logging agents and configuration files. Instead, you create a second container, a lightweight logging utility. You deploy both the web server and the logging container inside the exact same pod. The web server writes its logs to a shared storage volume. The logging container, acting as a sidecar, mounts that same volume, reads the incoming log files, and streams them out to your monitoring system. They operate as one integrated unit, sharing resources without muddying their individual responsibilities. When deciding if two containers belong in the same pod, ask yourself if they inherently need to land on the exact same machine and share an identical lifecycle. If they don't absolutely need to deploy, start, and die together, they belong in separate pods. That's all for this one. Thanks for listening, and keep building.